Okay, welcome everybody to the SPD seminar today. So today we have two speakers, Mykhaylo Shkolnikov and Jiacheng, both from Princeton. And they will basically talk about one subject divided into two parts. The first part will be given by Misha. So he obtained his PhD in 2012 at Stanford. Then he spent a few years as a postdoc in Berkeley before he finally moved to Princeton in 2014. So we are very happy to have you here today and look forward to your talk on a sharp interface limit in the Giacomin-Lebowitz model of phase segregation.
All right, thanks a lot, Carsten. So it's a pleasure to speak at Columbia, even if it is remote this time. Before I start, let me say that I think my internet connection is strong enough. So if you want to turn on your video and just ask questions during the seminar, that would be great. I think that would bring us closer to an in-person experience. Now, my talk today will be about a certain model from mathematical physics. And so to start with, I want to show you a video of the phenomenon that the talk will be about. So let me quickly switch here to YouTube. Okay, so the experiment that I will be talking about is about the phase separation in a mixture of two liquids that are immiscible. So a typical example for that is oil and water, right? So as we all know, if you put oil and water together, they tend not to mix. But the experiment that you can try out and that you will see in the videos, what happens if you actually mix in oil into the water, and okay, but we'll see in a moment what happens. So let me quickly play it. All right, so basically here, right, we're just pouring oil into the water, and as time goes on, you see these oil bubbles rising to the top and sort of the separation of the two liquids, right? And eventually all of the oil is at the top of the glass and all of the water is below it, right? So that's the type of process that we will be discussing today. And so let me start kind of directly with the mathematics and more specifically with the key object of the talk, which will be a certain free boundary problem. And big part of the talk I will spend on explaining how this free boundary problem is related to what you have seen in the video a moment ago. Okay, so before I write the formulas, let me draw a picture to describe this problem pictorially. So I will draw a time on the vertical axis here and space on the horizontal axis. And throughout the talk, the space dimension will be 1. Okay, so I'll explain from time to time what happens when you move to higher dimensions, but essentially we will stick to dimension 1 throughout the talk. And so in terms of the video, what you can think about is that we're trying to model the concentration of oil in this mixture that you saw, but we take basically averages on horizontal layers in this glass. And so we just want to know how the concentration of oil changes. So how these averages change if you go from the bottom of the glass to the top of the glass. Okay, so this brings you to 1 dimension. And of course, it's interesting to think about the actual multidimensional process, but I will stick to dimension 1 for most of the talk. And so this key object that I will describe in a moment will be a free boundary problem. So there will be a boundary evolving in time. I will write lambda for this boundary. My time variable will be s. So lambda of s will be the location of the free boundary at time s. And so roughly speaking, the way you should think about this picture is that I will think of having water on the left of the boundary and having oil to the right of the boundary. So imagine that you're kind of fairly far in the phase separation process that you saw in the video. So you can actually sort of distinguish the regions mostly occupied by oil and mostly occupied by water. And imagine for a second that there is a sharp interface. Okay, I'll explain this in much more detail in a moment, but think of lambda as a sharp interface separating water from the oil. Okay, so in this kind of toy view of what we saw in the video, you can think about the following problem, which, if you like, you could consider as a model for the concentration. Now, in my free boundary problem, I will write u for the unknown function. And so, morally speaking, you can think of u evaluated at s and y as the concentration of, say, oil in the mixture at location y, so let's say at height y in the glass, and at time s, of this phase separation process. Okay, I'll make this more precise a bit later, but for now, just think about the u as being this concentration. And so in particular, it will be a function taking values between 0 and 1. Okay, so 1 would be pure oil, 0 would be pure water, and you could have something in between, for example, a 50-50 situation with u being equal to 1/2. Okay, so in that context, consider the following model for u. Okay, so whenever we're outside of the boundary, so either within the oil region or within the water region, we will impose PD on our function u. So the PD might be familiar to many of you. So it usually goes by the name porous medium equation. It reads, the way I wrote. So there is a nonlinearity capital A that you apply to u, and then you take the second derivative in space. So that's the right-hand side. And so in this problem, this PD holds whenever you are not at the boundary. So whenever y is not equal to lambda s, and for all non-negative times. And so we'll have a free boundary problem, meaning that this function u, this concentration function, will be coupled to the motion of the boundary lambda, which itself is unknown. So both u and lambda are unknown functions. And the coupling between the two in this problem will look as follows. So there is a constant. Don't worry about the notation for a moment. So just think about the factor that I wrote as some constant. I'll explain a bit later, why I write this constant in the way I did. And then you have, so this constant will multiply two terms, which will be related to the flux between the two phases. Okay, so roughly speaking, the boundary will be driven by oil flowing from the water phase towards the oil phase, and by water flowing kind of into the water phase. So both of them will try to reach some sort of equilibrium for that phase. And so, formally, the type of flux term that we will look at will be the following. So we'll take the derivative of a nonlinear function of u. It's the same nonlinearity as in the PD, the same capital A. And so there will be one contribution from one phase, so from one side of the boundary. So that's the oil side. And you will have another contribution of a similar type from from the water side. So when I write lambda s plus and lambda s minus, what I mean is I look at my functions in the limits that I approach the boundary from the right and from the left. Okay, so that's the main free boundary problem. And on top of that, it will have some initial and boundary conditions. The initial condition I will ignore for the moment, let me omit it, but it will be important for us to keep the boundary conditions in mind. And so we will fix the two concentrations on the two sides of the boundary. And so rho plus, which was part of the constant in my free boundary condition, will be the concentration on the oil side of the boundary. And rho minus will be the concentration on the water side of the boundary. Okay, so essentially the way you should think about this problem is you have some nonlinear diffusion going on within the two phases, which describes how the concentration is changing. On top of that, you know, the boundary between the phases moves. It moves because there is a flow of water and oil across the boundary. So basically there is water leaving the oil bubbles and there is oil, you know, being absorbed into the oil bubbles. So that's this long parentheses in the boundary condition. And essentially, you know, whenever one particle of water or one particle of oil changes the phase, you have this sort of price of 1 over rho plus minus rho minus, because your concentration jumps from rho minus to rho plus as you go to the other phase. So that kind of hand waving explains, you know, how this problem relates to the picture and to the video. And so I'll spend the rest of the talk explaining, you know, the physics and the mathematics of this in much more detail. And in particular, what Jiacheng and I will explain is, you know, what U actually means in this problem. And what it will mean will be the large scale version. So it will describe the large scale behavior of the process that you saw in the video. Okay, so before I get to that, let me introduce the second main player for the talk, namely the Giacomin-Lebowitz model that the title of the talk alludes to. All right, so the Giacomin-Lebowitz model you can think of as yet another equation that tries to describe what is going on in the video. And as you will see in a moment, it attempts to give a much more precise description of what's going on in the video. So in this model, we still have an unknown function which will describe the concentration of oil in the mixture. However, this function rho in the model will not solve a free boundary problem, but rather it will not distinguish the two phases, right? So it will take into account that, you know, strictly speaking, there is no pure oil and no pure water in that video that you have seen, right? So at any location in the mixture, you have, you know, some sort of concentration between 0 and 1. And in fact, there is no strict separation between the two phases, right? So if you zoom in on, you know, a little bit of the mixture, you know, somewhere in this glass, you will not see, you know, just pure oil or pure water. You will see some mix of the two at some concentration, right? So maybe closer to a pure oil or closer to pure water, but, you know, the concentration will be strictly between 0 and 1 at all places. Okay, and so what Giacomin and Lebowitz suggested is the following equation for how this rho changes over time. So the equation is, you know, much nicer and shorter than, you know, this long free boundary problem that I stated before. So I think the model is quite beautiful. It sort of captures the process that you saw in the video just by one equation. And the equation goes as follows. So it's yet another PDE, right? So you have again the time derivative on the left, a second space derivative on the right, and some nonlinearity. However, in this equation, you have a non-local term. So you have the second term appearing, which is a convolution of the unknown function rho of the solution with some kernel J. And so J for us, and in the model, is a non-negative kernel. It will integrate to 1. That's not necessary. It can be a general L1 function, but it will simplify the notation here and there. So I'll make it integrate to 1. And on top of that, we will assume that it is symmetric about 0. Okay, so take your favorite PDF, let's say standard normal PDF, and you can think of J as that kind of kernel. And so within their frameworks and their model, I can now actually explain much better what the physics behind this model is. So in a sense, it's a much more reasonable model for what you have seen in the video. Okay, so the reason for that is that you can think of the equation for rho as a gradient flow for a certain energy function. So let me write the functional first, and then I'll explain how you can view the right-hand side of the PDE as some sort of gradient of this function. Okay, so consider the following functional. So it will stand, so f of rho will stand for the energy of some concentration profile in the mixture. And it will be of the following form. So I will have one term where I will be integrating some nonlinear function of rho. So this f here corresponds precisely to the f prime that you see in the equation. So f prime is the derivative of precisely this function f. And then I have a second term which will involve the kernel J, and it looks as follows. So it's this double integral in the second term. So let me rewrite the energy also in a different way, since this will be enlightening for the discussion in a moment. So I claim the expression I just wrote can be also written as follows. So I'll absorb a quadratic term into the first integral, and I will write the second term as 1/4 of the double integral of the following double integral. All right, and so now, okay, so first of all, it's easy to convince oneself that the two expressions for the energy are the same, because if you look at the square over here, right, if I just multiply it out, the mixed term will give me precisely the double integral I had before. And the two quadratic terms will be the same because of the symmetry of J, and they will cancel out precisely with this quadratic term that I placed in the first integral, right? So these two expressions for the energy are actually the same. However, the second expression is kind of physically much more enlightening, right? So, so let me focus on the first term, and Jiacheng will say more about that, but let me just draw one picture. So, of course, the behavior of this energy will depend on how this function f of rho minus rho squared over 2 actually looks like. So it depends on the choice of f. And the choice we will make, and that's again taken from Giacomin and Lebowitz's work, is of a double well forms that will look somewhat like this. And so the point is that this energy functional f minus rho squared over 2 will have two minima at rho minus and rho plus. And those stand precisely for the two equilibrium concentrations in the two phases, right? So physically, what this is saying is, given the conditions, so the temperature and pressure in our mixture, there is an equilibrium concentration in the oil phase, so an equilibrium amount of water within the oil, and at the same time, within the water, there is an equilibrium concentration of the oil in the water, for any given temperature and pressure that are fixed in this model. All right, so you have these two minima, and so if you look at the second expression for the energy, so this expression here, you realize immediately that if I choose rho to be constant at rho plus or constant at rho minus, the energy will be equal to 0, right? So it will be minimized. So the two kind of preferred configurations for my mixture is just to be, either in equilibrium within the oil phase or in equilibrium within the water phase. But in the situations that we will look at, we will be sort of in a frustrated situation. So we will look at an actual mixture of oil and water where, we will not allow, the whole mixture to be constantly at rho plus or constantly at rho minus. So rather, we will look at, initial conditions where at the bottom of the glass, we will be at rho minus. So deep into the water, you will be at the equilibrium concentration for water. Deep into the oil, so at the top of the glass, we will be at rho plus, but in between, the concentration will have to somehow go from rho minus to rho plus. So we will never be at either of the two global minima of the energy function, but rather, somewhere else in the state space. And what the equation on top will be doing, it will follow the gradient of the energy functional. So now it's sort of more convenient to look at this first green expression for the energy. And so a quick computation shows you that if you take the functional derivative of this green expression with respect to rho in the space L2, you would get precisely this nonlinearity here. Okay, so the f prime will come from the first term and the convolution will come from the second term. And if you took the functional derivative in the Sobolev space h to the -1, you would end up with the negative of the right-hand side of the PD. Okay, so one way to think about this model, the equation for rho, is that we're following the functional gradient of capital F, and so our phase segregation process is trying to minimize the energy, and so follows always the direction of the steepest descent of this energy function. All right, so that's the motivation, and I will leave additional details to Jiacheng. He will sort of zoom more on this part in his talk. Instead, what I will do is I will explain how this problem, this model, relates to the free boundary problem that I wrote before, and sort of announce our main results, and then again, give the details and the highlights to Jiacheng for his part. All right, so what is the relationship between the two models that I have described? Well, in the second model, you can again sort of draw a picture analogous to the picture that I drew in the beginning. So you can again draw time here, space here, and you can think of the second model as doing the following. So it again models the concentration. So let me kind of put in the two values for the concentration, rho minus and rho plus, into this picture. And let me kind of draw the type of concentration profile. Actually, I apologize. I want to put the concentration here on the y-axis, right? And so the type of profile that we're interested in due to the video that I have shown you are the following. So we're interested in profiles that look somehow like this. So, think of kind of the negative infinity boundary as the bottom of the glass in the video. Think of the plus infinity boundary as the top of the glass. And so as you approach the bottom of the glass, you're getting closer and closer to this equilibrium concentration in the water phase. So you go to the top, you approach the equilibrium concentration of the oil phase. And you have kind of three regions in this picture, right? So you have basically water, right? So with some kind of oil impurities on the left, you have basically oil with some water impurities on the right, and you have an interface region that separates the two, where the concentration actually goes from being close to rho minus to close to rho plus. Now, the equation for rho describes the evolution of all three regions in some sense. But if you want to really understand how the interface region is behaving, so how it moves, it's sort of difficult to infer that directly from the model, from the Giacomin-Lebowitz model itself, because you would somehow need to understand. So first of all, you would need to define this interface region. You would have to set, some thresholds to even define this interval. And secondly, even once you have defined it, you would have to describe, how this interval is moving as time evolves. And so, it might grow, it might shrink, and it would not be completely obvious, certainly how the dynamics of this interval will look like under our model. And so in order to describe the dynamics of the interface region, what is proposed already in the paper by Giacomin and Lebowitz is to look at the so-called sharp interface limit. So that sort of fills in the last words in the title of my talk. Right, so to study this interface region, what the tool suggests is to look at a version of rho where you zoom out of the picture, right? So essentially imagine standing sort of very far from this picture. And if you zoom out, so if you think about the large scale behavior, you can imagine that this interval describing the interface region will just look like a point to you, right? Standing far away. And so if you look at a large enough scale, what you will be trying to model or trying to understand will be the dynamics of, just one point describing, where the oil phase separates from the water phase. And this will be, much more tractable. So for that purpose, the tool look at a rescaling of the concentration function. So here it turns out that the diffusive rescaling is the right thing to do. So we will choose epsilon small, so it will go to 0 eventually. And, zooming out will correspond to scaling, by negative powers of epsilon. And so turns out that the diffusive rescaling is the right thing to do in this model. And so the main conjecture, which is sort of the highlight of the series of 3 papers and also the highlight of this talk, is what happens when you send epsilon to 0, right? So you kind of zoom out further and further. You're supposed to see now a sharp interface emerging. So this interfacial region, shrinking down to a point. And what you want to know is how does this shrunk region, so this point, move in time. And so the conjecture that they have formulated is that, under suitable assumptions on the initial condition, this limit does exist, and that it's given precisely by the free boundary problem that I had on my first slide, so in the very beginning of the talk, right? So the claim is, once you send epsilon to 0, once you zoom out completely, the interval will shrink to a point, and the evolution of this boundary between oil and water will be described by the free boundary problem that I mentioned in the beginning, right? And so, if you're interested sort of in the physics of it, think of U as an approximation of rho epsilon. So think of this statement as the statement that you can approximate rho epsilon by U for small epsilon. And what this means now in terms of an actual physical process is that we're thinking of the layer separating oil and water as sort of a thin film, right? And you do see it in the actual experiment, right? You see these oil bubbles and sort of a thin film around them, where you have a mixture of oil and water, and then on the other side of this thin film, you have the water. And so if you approximate rho epsilon by U, you're basically saying that you're kind of taking the abstraction that this thin film is actually, just a hypersurface. So its thickness is equal to 0, and you're approximating the evolution of this actual layer by the approximation of this idealized hypersurface. And of course, if you're just in dimension 1, then you don't really have a hypersurface. You just have a point that moves dynamically in time. So that's the conjecture. And
I have a question, sorry.
Sure, go ahead. Yeah.
In what type of space or topology do you have this convergence?
That's a very good question. So I guess one way to think about it for now is that you have just point-wise convergence. Okay, so that, for at any point, if I fix, S and Y, I will converge to U of S and Y.
Thank you.
And right, so you can basically think of both U and rho epsilon as classical solutions of the corresponding PDEs. So Jiacheng will be more precise on that, but think of them as being classical solutions and as having pointwise convergence of the functions at least. Right. Now, thanks for the question. So right, and so in the paper, Giacomin and Lebowitz present a justification for this conjecture or derivation, which is based on a formal asymptotic expansion. So it's not a rigorous proof, but it strongly suggests that this conjecture should be true. And so today we will be talking kind of about the resolution of this conjecture, so the mathematical proof of it. And if you sort of think about the gap between the formal asymptotics and the rigorous proof, there are two aspects, so two main obstacles, 1 and 2, to the rigorous proof. So one obstacle that you have to overcome is that, first of all, it was not clear at the time they wrote the paper, and in fact, until our work, that U is indeed well defined. Okay, so I wrote down some kind of free boundary problem for this function U, but in fact, it was open, at least to the best of my knowledge, whether this free boundary problem actually has a solution. Okay, so, and whether the solution is unique, right? And so if you want to make the conjecture precise, you better have a unique limit U that you will put into this conjecture. Okay, so that's, the first mathematical obstacle to making this precise. The second one is that you need to justify the formal expansion that the two did. And the obstacle there is that terms in this formal expansion involve u and its derivatives. So you need to know, on the one hand, that u actually is well-defined itself, but on the other hand, you have to know that u is smooth enough that these various derivatives that enter the formal expansion actually make sense, in some appropriate space, right? So basically, the second obstacle is to show that u is smooth enough to justify the expansion. Okay, so I will leave the second item essentially completely to Jiacheng. So he will say a bit about that in his talk, and I will only discuss kind of the first obstacle in my part. And before doing that, let me mention briefly what our main results are. Again, Jiacheng will have the details here, but I want to say quickly what we can actually prove here. So we have two main results, if you like. So on the one hand, if you are in the one-phase version of the problem, what it means is that, so what I mean by one-phase version is that I take a rho, maybe it's better to say it with u, I take u to be constantly equal to rho minus in the water phase. So in other words, imagine that I look at the simplified version of the conjecture and the whole setup, where within the water phase, I assume that the concentration has already equilibrated. So it has already reached this equilibrium concentration of rho minus, right? So that's supposed to happen after you run the phase segregation process for a long time. But let me assume that you have already reached the equilibrium concentration on one side, but on the other side, so in the oil, the concentration is still evolving according to this nonlinear heat equation or porous medium equation. So in that setup, we have a full proof of the conjecture, meaning more precisely that we can resolve both of these obstacles 1 and 2, right? So in this case, we can show on the one hand that indeed u is well defined, and on the other hand, we can show that it's a classical solution, so it's in a nice enough space that you can justify the asymptotic expansion and prove that u is indeed the limit of rho epsilon, so of the scaled concentration in the Giacomin-Lebowitz one. So that's one result. Our second result concerns the general case. Okay, so by general, I mean that we're not making this one-sided assumption here, but we're still in one dimension. So let me emphasize that. And in that case, we don't know how to resolve 1, but we can resolve 2, meaning that if there is a proof at some point that there is a smooth enough function u, then we can indeed justify the asymptotic expansion and justify, completely rigorously that we have the convergence in the conjecture, right? So this is a partial result in that case, and the missing bit there is to show that u is well defined in general, which we can only do in the one-sided case. All right, so these are our results. And as mentioned, I'll spend the last, I guess, 10 minutes or so saying a little bit about this obstacle 1, and specifically in the one-phase case where we can resolve this case and this conjecture. All right, so let me focus kind of on this obstacle. Yes, go ahead.
So can you remind me, like what's the difference between this one-phase version and the general
Right,
phase?
exactly. So if I go back, for example, to this picture here, right? So I have this unknown concentration or unknown function u on both sides. And so the one-phase case is the case where in the water, I set u to be constantly equal to rho minus. So if you like, I start with an initial condition where u is constantly equal to rho minus on one side of my free boundary. And then I run the equation, and it's not hard to see that if I start at the equilibrium concentration in the water phase, it will stay at the equilibrium. So u will be equal to rho minus everywhere to the left of the boundary. And so in that case, I have a simpler problem because I am now only describing what happens to the concentration in the oil, so to the right of the boundary. So instead of having this two-sided version, I end up just with a one-sided version of my free boundary problem.
In the general case corresponds to start like the left-hand side with some
exactly. So the general case, you start on both sides, away from equilibrium in general. So you have some initial condition which is not constant in general on both sides. Right, in terms of rho, you can think of this picture here. So you kind of start near rho plus, but with some fluctuating concentration to the right of the interface, and you start near rho minus, but with some non-constant concentration on the other side. So your concentration will follow some sort of diffusion equation on both sides, and the change in the concentration will drive the motion of the boundary. So you have essentially kind of two PDEs on the two sides, and they're coupled through the motion of the boundary.
I see, thanks.
Sure, you're welcome. All right, so and the last bit of my part, let me focus on this one-phase version and say just a little bit about its analysis and a little bit how it relates to probability and also why it is simpler and why we can analyze this version but not the general case. Okay, so to do that, let me just very quickly write out the one-phase case. So write out the free boundary problem in full details. As I just mentioned, in that case, you just need to worry about the concentration to the right of the boundary. So it points to the right of lambda s. And you have the following boundary conditions, I guess initial and boundary conditions. So on the one hand, as before, we are assuming that at the boundary, I will be always at equilibrium for that phase. I will have some initial condition, which I will write as rho plus minus some function of y, which I will call G2, right? So I really think about the initial condition as some sort of deviation from the equilibrium concentration, and G describes this deviation at different points in space. And finally, I need the free boundary condition or the Stefan condition. So that relates the velocity of the boundary to various quantities in the problem. So I will have now only one flux term because I'm in the one-sided case. And so I look at the flux across the boundary, but now just from right to left. And I multiply this sort of nonlinear version of the flux by the same constant that I had before. Okay, so that's the one-sided version of my free boundary problem. And in particular, there is kind of a notable special case of this problem, namely the case where the actual PD in the problem is linear rather than nonlinear, right? So if A happens to be a linear function of U, let's say U over 2, my PD will just become the heat equation. And in that case, this problem boils down to what is known as a supercooled Stefan problem. All right. So this linear choice of capital A, it's not interesting in the context of phase segregation, but it turns out to be interesting in a different physical setup, which I will omit to save some time. But you know, it's again a physically meaningful problem just for a different experiment. And so I want to briefly focus on this linear case because you know, this will allow me to explain the connection to probability and also, you know, give you some intuition for how the solution actually behaves and how we can analyze it. All right, so so first of all, let me connect this linear version of the one-phase problem to probability. So here is how you can think of it probabilistically. Okay, so even though there are no SPDs in my talk, there are at least PDs and something stochastic, so you know it fits at least somewhat into the seminar. Right, and so probabilistically, this last problem I have described can be thought of as follows. So you have this free boundary lambda and my one-phase problem. Okay, so it depends on time. And here I have space. Now, let me draw this initial condition. So before I wrote the initial condition as rho plus minus some function G2. So now I will sort of flip the picture and just draw G2. So I'll just draw by how much I'm deviating from the equilibrium concentration. And so think of G2 now as some sort of probability density. And so if you think about the problem this way, then you can formulate it probabilistically by saying that you start off with sort of an ocean of particles, and I'll put more particles, you know, where this density is high, fewer particles where the density is low. And all of these particles will start doing Brownian motions as time evolves. So these blue path should stand for a path of Brownian motions. Should look like a Brownian motion. And so probabilistically, you can think about the problem as follows. So you start these Brownian motions. They will hit the free boundary at some point, because Brownian motion is recurrent, of course, in one dimension. And whenever they will hit, they will be absorbed at the boundary and will move the boundary by an infinitesimal amount. So this supercooled Stefan problem, or the linear version of my problem, can be phrased as follows. So you start with some initial profile, some initial density G2. You start running Brownian motions from all points of the positive half line, and you put more Brownian motions at points where this density G2 is high. And you run all of them. For each one of them, you absorb it once it hits lambda, and when it is absorbed, it will advance lambda by some infinitesimal amount. Okay, so if you want to make this more precise, you can think about it as follows. Instead of thinking about many Brownian motions, think about a representative one. So I draw a random point in space according to this density G2. I run a Brownian motion from that point. I wait until it hits lambda, and once it hits lambda, I will advance lambda at a rate of absorption, right? So the probability that I will be absorbed before a certain time will be proportional, or the way I said it, will be equal to the value of lambda at that time. Okay, so that's kind of the probabilistic picture behind the linear problem. For the nonlinear problem, you can do something similar, just that you will have to run certain diffusions instead of Brownian motions for your particles, but otherwise the description will be the same. And so in particular, this allows you to use large toolbox from stochastic analysis to study this problem. And in the linear case, we have recently worked out well-posedness of that problem. When I say we, I mean Francois Delarue, Sergei Natochi, and myself. And the paper has been on archive since last year. What we have shown in that paper is that in this linear case, you have indeed well-posedness of U. And in addition, what we have shown is that it has, so we have somehow described the solution U in quite a bit of detail. And in particular, it turns out that if the sup norm of the initial condition is strictly below 1, actually, sorry, have a different normalization here. So let me say that again. So if the sup norm is less than rho plus minus rho minus, so less than the inverse of the constant that I have over here, one of our results shows that in fact, U will be a classical solution of the free boundary problem. So in general, you have to formulate a different concept of solution, which we call probabilistic solution in our paper. But in the special case where your initial condition is somehow small enough, the solution turns out to be classical. And so now if you sort of think about the task at hand here, right? If you go back to the nonlinear problem, you realize that in this context, we're sort of tackling a problem which is on the one hand harder because we have the nonlinearity, capital A, in our PDE, but on the other hand, it's actually simpler because by design of this problem, so due to the physical meaning of this problem, the initial condition, so the G2 over here, is necessarily less than rho plus minus rho minus, right? So if I go back to my picture, right? So G2 describes the deviation from the equilibrium concentration in the oil phase. And so, just the way the problem is set up, this deviation cannot reach the value rho plus minus rho minus because otherwise I will be at rho minus or even below it. So I will actually be in the water phase and not in the oil phase. So, this whole phase segregation setup brings you into this more regular regime of this free boundary problem. So despite the fact that we have a nonlinearity in our PDE, in some sense, our life is simpler here because we can now expect to have even classical solutions of the free boundary problem. And so the last thing I want to say is that indeed, what we show in our work with Jiacheng and Sergei is that this free boundary problem has a classical solution. So this function U exists classically, and this sort of goes half the way in terms of proving the conjecture, and then the second half of the paper makes sense of the formal asymptotic expansion of Giacomin and Lebowitz, and justifies that what they're doing it can be made rigorous, so all the functions appearing there live in the right spaces and combine to a nice smooth solution, and therefore this completes the proof and gives us the full conjecture, at least in this one-phase case. All right, so let me stop here and again emphasize that Jiacheng will take over in 5 minutes, I believe. And so he will zoom into this sharp interface limit portion and tell you in much more detail what the actual rigorous statement of the result is, and also maybe say a few words about the proof if he has time. So thanks a lot.
So thank you very much for this very interesting talk.
Thank you.
Other questions from the audience? So I have maybe a question. So okay, suppose you're in the linear case, the last one that you've mentioned. Does it make sense to pose the SPDE problem? So if you add noise on the right-hand side, are there any known results about existence of solutions and so on?
Okay, that's a good question. So, right, so, okay, so in the linear case, if you just put additive noise, right, means essentially you're putting in a source into this problem, right? So it's kind of similar. Okay, it depends a bit on what sort of noise you want to put, but if you put something, either Brownian-like or something like white noise, then the closest result I know is a paper by Amir Dembo and Licheng Tsai, which looks at the linear problem with an initial condition given by white noise. So that would basically correspond. So presumably, along the lines of the analysis, you will be able to also tackle a source of white noise type. And it sort of lies just outside our paper with Francois and Sergey, because we assume kind of some regularity on the initial condition. It's not a lot of regularity, but it rules out sort of Brownian-like initial conditions. So yeah, so that paper would be the closest to what you're thinking about. So in the linear case, there is, for example, a well-positiveness result in their work when you start with this Brownian-like initial condition. For the nonlinear case, I'm not aware of any work with initial conditions that would look Brownian or like white noise. So I believe any result you could get there would be completely new.
Okay, thank you.
Sure.
Further questions?
Could I ask a question?
Sure.
Misha, thanks for the talk.
Hey, sure.
Sorry if I missed this, if you said this already, but is there an easy way to explain the connection between how this function A arises from the scaling limit from the energy function?
Right. So, okay, I could leave it to Jiacheng, but let me just say it sort of in one sentence. He will say more about it, I believe. So basically, right, if you look at the first line in the slide, right, it looks already kind of like the PD that you have in the limit, right? So you have second derivative of some nonlinearity, just that this nonlinearity is non-local before you take the limit. And so what happens, to say it briefly, when you rescale, this kernel J will be scaled in such a way that it becomes more sharp, right? So you will get something like epsilon inverse of j evaluated on epsilon inverse times x. So you're kind of zooming out and seeing kind of this sharp kernel j now. And so in the limit, therefore the convolution should, ends up just becoming the convolution with a Dirac delta function at 0. So it's not actually a convolution anymore. And you will just end up with rho in the limit of that term. And so therefore you get kind of the second derivative of f prime of rho minus rho. And the function a is precisely that. So it's precisely f prime minus the identity function.
Thank you.
Sure.
Are there further questions? We have time for a last question. Okay, so if not, let's thank Misha again.
Thank you.
So we're going to take maybe 2 or 3 minutes break and then move on to Jiacheng's talk. Okay.
Should I start sharing?
Yes, you can
Yes,
start.
yeah, I think I unshared, so you should be able.
Okay. Can everyone see the Wikipedia?
Yes, I think you can still put it on full screen.
Yeah. Can I just stay in this way? I guess I'm more comfortable with it this way. I guess.
Okay, if you prefer, sure. So are you ready to start?
Yeah, sure.
Okay, so our second speaker today is Jiacheng from Princeton. He's a 4th-year PhD student with Misha, and he will basically continue with the talk that Misha has presented in the first part of this seminar.
Yeah, thanks, Carson, and thanks, Misha, for the talk, and thanks for the invitation here. So basically, I will continue talking about this sharp interface limit for Giacomin and Lebowitz model of this phase segregation. So basically, I will state the background story again about this phase segregation phenomenon and about this sharp interface limits. And again, if I have time, so I will talk a little bit about this main results. As Misha said, this is the star 1. Basically, the one side is Stefan problem, and the star 2, the proof of the actual sharp limit interface. So yeah, for the phase segregation phenomenon, so basically the starting point is we have 2 materials, material A, material B, like we see in the video, such as like water and oil or water and air. And if we denote this rho being the concentration of A, then basically in the video, we can see these two materials basically separate away from one surface, and above the surface is mostly A, in the sense that the concentration A is approximately this rho plus, which is close to 1. And above the surface, mostly it's B, maybe with a little bit A inside. That means this rho is approximately rho minus, and this rho minus is close to 0. And in the picture, I just wrote 1 6 line for this surface, basically means the interface, but actually we can, this is just not a line, it's an interfacial region. So we zoom in, we can see that inside this interfacial region, the concentration of this A basically vary continuously from this rho minus to this rho plus. And just to look at this zoomed region, again, we will focus on this one-dimensional case. We can see that this rho will satisfy in the left parts. This rho will be very close to this rho minus, which means this rho is basically this region is basically material B, and inside is A. This rho will be very close to this rho plus. Means that in this region this is mostly A, and inside this interface region this will like vary from rho minus to this rho plus. And this is just like a fixed time status of the rho. And actually in Giacomin and Lebowitz paper in 1997, this evolution, they deduce an evolution equation for this rho. I think Misha just talked this before. This evolution equation is partial. The time derivative of rho is equal to the second space derivative of like f prime of rho minus the convolution of J and rho. And inside here, this J and F will depending on the depending on temperature and pressure and some like environment variables here. Yeah, so this equation will somehow explain how the rho will evolve along this time. And we will spend a little bit more time about on this equation here. So mathematically speaking, this non-local evolution equation comes from rescaling some particle system. This is just one conclusion from Giacomin and Lebowitz 1997 paper. And if we somehow like rewrite this equation in the sense that we can rewrite it as the second derivative of the functional derivative of a free energy functional f, which can be written in this way. So this just this f is just the integral of this nonlinear function of rho, and minus somehow this interaction connected with this J. Yeah, so in this sense, we can see this rho as a gradient flow, in the sense that as time evolves, somehow the logic for this rho is that this rho will move towards some rho such that it will minimize this f. Therefore, let's look at more about this f. So if we assume, as Misha said, we assume the integral of J being 1, then we write this f. I think Misha did this before. So basically, we write this f. It can be written as some function, or some other function of fc times plus this like J times the difference of rho x and rho y. In this sense, so why is this a better way to see this thing? As you can see, if we assume like this fc only have one global minimum, for example, rho 0 here, then we plug in this rho 0. This one will just be 0, which is the which minimize this integral, and in here this is also a global minimizer. So basically, if fc has only one global minimum, then this rho equal to this global minimum somehow minimize this function of rho, in the sense that this rho equal to just one global minimum will be a stable state. But in our case, since we have a phase segregation, we will assume this fc having two global minimum, in the sense that, so if rho equal to one global minimum, let's call it rho minus and the rho plus, either way, it will give us a minimum of this f rho here. So therefore, it somehow tells us that to have a stable version of this energy, this rho will at one side being very close to this rho plus, and at the other side being very close to this rho minus. Just as I said before, for the phase segregation phenomenon, FC must have a double well structure. So there are two global minimum rho minus and rho plus here. But as long as these two like phase are always exist, there will have some interface region which will travel from this rho minus to the rho plus to make it stable. And the other part for A and B will just remain around this rho minus and around this rho plus. This is how the illustration for this FC here. Okay. Yeah, and let's go to this sharp interface limits thing. So what is this sharp interface? First, what does this sharp interface limits means? It means that the phase domain are very large compared to the size of the interfacial region, in a sense that like in the picture, this A and B are basically one region, and if we look it in a like long range, this A and B will mostly be like a region, but for the interface, it's just one line. So it means that A and B are like much larger than this interfacial region. And this will initiate our idea to rescale this rho to see the collapse of this interface, in the sense that rather than interfacial layer after this rescaling, this layer will just collapse to one point. And this helps us, as Misha explained before, this helps us to analyze the movement for this interface. And in order to, so basically, as we see in the picture, so we have this like more general case where we zoom out this interface, and we will have like a continuous variation of this rho, and we do this rescaling to force this interface being narrow. And inside here we'll just as epsilon goes to 0, this one will just like look like a jump from rho minus to this rho plus for the interface region. Okay, so assuming this rescaling point, so mathematically speaking, recall our non-local evolution equation, and we will do this rescaling on space. But as you can see, if we did this rescaling on space, basically we need to see the movement in a like pretty large range of time. So we need to do this rescaling on time, and we did the diffusion rescaling in the sense that this epsilon. If we did epsilon to the -1 to the space, we'll do epsilon to the minus order of 2 on t. Then after this, after this rescaling, this PDE will just like somehow it become much similar, but the only change is that this j, rather than this j, will have a j epsilon, which is a rescaling of j, in the sense that as Misha explained at the about dense question, it will become more sharper, and it's much sharper, and it will basically converges to a delta function. And therefore, at least intuitively, this rho star as the limits of rho epsilon should satisfy for this integral as epsilon goes to 0, this is just j epsilon, and it will converges to a delta function. The no local term will become local in the sense that it will just drop into rho. So therefore, this rho t, the time derivative of the limit rho star will just be the second space derivative of f prime of rho star minus just one rho. And this is exactly the same as this fc prime of rho star. This fc will serve as the chemical potential here.
So this j can be arbitrary, basically, like as long as like the scaling goes to delta function.
Not exactly, I guess. So yeah, so there is much details about this j by like the in order to have this limit, in order to have this sharp interface limit, I guess basically the most natural assumption would be like j is set symmetry around this 0, but I didn't put this one in the slide since I don't think, at least for now, it's not that important here. But yeah, but it needs some assumptions here.
Okay.
Mm-hmm. But the assumption is basically quite, I think it's quite loose. It doesn't need some explicit shape of j or something else. You can, as long as you have some like symmetry, that should be fine. Okay, so let's go to our, so by this term, we somehow know at least the PDE equation for this limit of this rho. And now let's go to this limiting conjecture of the Giacomin-Lebowitz model here. So record this PDE form. Assume first this phase segregation for the limiting initial condition. That is, we can assume this rho 0 epsilon as the limiting and as the initial condition of this rho epsilon will converge to some rho naught star in the sense that this rho star will have when it's approach this rho 0 at basically this A material, this will converge to this rho plus, and at this B material at this interface region, it will converge to, oh sorry, there's a typo here, it should be rho minus here. So basically force the limiting initial condition such that this interface region will have a jump from rho minus to this rho plus at this interface. So this is the assumption for the limiting initial condition, and the limiting conjecture would be rather than a more obvious way about this PDE, about the PDE form of this rho, which we somehow deduced before. It will also have other property in the sense that it will always have this lambda t as an interface, and among this lambda t, this rho xt will converge for example, if we look at just one dimension to the left, it will converge to rho minus, and to the right, it will converge to this rho plus, and at this lambda t, it will have a jump. And also, the most important thing is that the movement of this lambda t, in the sense that the time derivative of this lambda t will be determined by basically the change of this potential, chemical potential, which means this Fc dot of rho near the boundary, near the interface, to the left and to the right. And this rho minus and rho plus will somehow represent since it will need to have a jump from rho minus to this rho plus. Therefore, as long as the jump is higher, then the movement should be smaller here. So this is how we interpret the movement for this interface. And of course, the initial condition will converge to the initial condition we drew before. So this was the limiting conjecture. This was the limiting conjecture in the Giacomin and Lebowitz paper. And as Misha said before, basically the star 1 and star 2. So first of all, in our paper, our main result would be first to make sense of this equation, at least in some regime. And also we want to make sure, or we want to make sense of how this convergence work, or how can we prove this convergence rigorously rather than just having a formal assumption, a formal asymptotic expansion there. And I will explain that formal asymptotic expansion in a while. But the thing is, in our work, basically we make sense of this equation and also prove the convergence more rigorously. Okay, so as I said before, the first result would be record our this limiting equation, and we assume the first result, we just assume at the right part, basically in the water region, we assume this rho minus rho at the initial condition, this rho is always equal to this rho minus. Then this limiting equation will reduce to a one-sided Stefan problem if we did a change of variable, in the sense that it will become partial t of rho, again with some change of variable, or change of function f tilde c, and we will have at the boundary, this will converge to 0, and the boundary will move, the free boundary problem will move along in a Stefan term here. I think Misha spent a lot of time about explaining this one and how to connect this one to the super cool Stefan problem when we consider the linear case. So basically, more general setting in our case would be, we will consider a nonlinear Stefan problem in the sense that we have this AU, which answered Dan's question. This AU is just FC prime in the sense here. And at the boundary, this U is 0, and we have initial condition, and also the movement of this boundary will be corresponding to the time to the derivative at the boundary of this function. So we have existence and uniqueness results of this equation, which solves at least part of the first questions, in the sense that we make sense of the limiting. We make sense of this limiting equation here in a special case where we take one-sided being the equilibrium state. Okay, so the other part, so the other part of our work is basically the proof of the sharp interface limits. So I will first spend a little time discuss about this formal asymptotic expansion that they Giacomin and Lebowitz propose. So they will have basically an inner and outer expansion here, in the sense that for this inner expansion, even though we work with this rho epsilon, as you can recall, we will still zoom in for the interface region, which corresponding to the inner expansion. And for this inner expansion, we consider this inner expansion in terms of like Taylor expansion for this rho 0 and plus epsilon rho 1z and rho epsilon square rho 2zt. But here this z is no longer like zoomed in z, it's just no longer like the zoomed out x, it's just a zoom in z, in the sense that it has a change of variable with order epsilon to the -1. And also we have an outer expansion, in the sense that we look at the actual rho epsilon, and this we at least argue that this rho epsilon xt would behave like this rho 0 tilde plus epsilon have another Taylor expansion here, rho 0 tilde plus epsilon rho 1 tilde plus epsilon square rho 2 tilde. And so basically our limiting result will focus on this picture here. So on the on the picture below, and this rho 0 tilde, as you can see, as epsilon goes to 0, would be indeed our limiting equation. So at the very beginning, we will assume existence for this rho 0 xt for the proof of the for the proof of the sharp interface limits, which of course this rho 0 tilde, when we look at the one-sided cases, is exactly the first result of our work, basically the existence and uniqueness for the one-sided Stefan problem here. Okay, so to give a very quick sketch of our proof, again, I want to mention that in here, this inner expansion and outer expansion is basically, this inner expansion and outer expansion is somehow constructing about this rho 0 and rho epsilon and also this rho tilde 0, rho tilde 1, and rho tilde 2. So therefore, our sketch of proof, the first step of our proof would be the construction of such expansion functions, in the sense that how can we construct rigorously about like the inner expansion and the outer expansion, in the sense that how about the existence of rho I and rho tilde I. So for the outer expansion, as you can see, this is just like for the outer expansion, it will behave very much like the limiting process. Therefore, it will be the solution of some parabolic or some Stefan problem here. But for the inner expansion, since we did not do the non-localized version, so we will be working at some non-local equation ODE. Basically, we will try to find some functions about this non-local ODE here for some G and H and J. So this rho is the actual solution we are interested about, but this G, H, and J we can like a priori given, and we want to discuss about the solution of such equation here. And after we have this inner expansion and outer expansion, we will glue the inner expansion and outer expansion to get some like glued function. So to have this glued function, basically for this inner expansion, we need at the boundary, they should be match the boundary of the outer expansion. So in here, we will need to match the boundary of the inner expansion and the outer expansion. And also for this glued one, if we plug inside the non-local equation for the rho epsilon, it will be very much like this rho epsilon, except that it will have some arrow term. So this is some this is some properties for the glued one. And the final step would be approximate this rho epsilon by the glued function, and therefore automatically this rho epsilon will converge to this rho tilde 0, which is the actual limiting function here. So this is basically the sketch and the big idea of our proof. Of course, there are some detailed technical parts of it I will not include in today's talk, but basically this is the big picture and the big idea of our work. Yeah, I guess that's it. And thank you for listening.
Thanks a lot for this very nice talk. Questions?
Jiacheng, thanks for the talk. And I have a question. Can you explain a little more detail about the inner and outer expansion in this physics heuristic? Like I don't quite like get like where they're coming from.
Okay, so basically for the inner expansion, we want to look at this, how does this interface evolve as this epsilon goes to 0? So, but actually, if you like do the rescaling, during the rescaling term, this interface basically becomes a step function, right? The interface here will just be a jump function from rho minus to this rho plus. But if we zoom out, I mean, if we zoom in for this inner expansion, the magic things here is that, so actually Giacomin and Lebowitz also mentioned that for this interfacial region, after we zoom out, this rho 0 ZT will behave like a stationary solution for the stationary solution for the PDE that this rho epsilon satisfied, and basically it will remain the same it remains the same shape for each epsilon here. So this is in the sense that even though we did the zoom in, zoom out makes the interface, the function inside this interface region become a jump function, but after we zoom out, this will remain the same after we like zoom out this function. So this is for the inner expansion, and for this outer expansion, this is just approximation for the actual function we are considering about. So basically this outer expansion, the main part for this outer expansion is this rho 0, which corresponding to the limits of our problem. That is the Stefan equation here. Does that make sense?
Yep. Like part of, yeah.
Further questions?
Yeah, quick one just to follow up on Year's question. So is it true that rho 1, rho 2, and so forth are going to be given by solutions to explicit PDEs? Homogenization theory?
Rho 1 and rho 2. Yeah, I think so. So basically rho 1 and rho 2 will be given by, as inner expansion, it will be given by some solution to the ODE, and then times some function of t. But for the outer expansion, this will indeed be some solution with some parabolic PDE solution. And actually I guess only for rho 1, this boundary is a free boundary term. Basically, this free boundary lambda will be determined by this rho 1, and for the rho tilde 1, rho tilde 2, the boundary is given by this like lambda 0 here. So we will be no longer worry about the free boundary problem, which makes the existence of rho tilde 1 and rho tilde 2 much easier than this rho tilde 0.
Okay, thank you.
Further questions? Okay, so if there are no further questions, let's thank Jiacheng and also Misha again for the very nice presentations. So in 2 weeks, we will not have a seminar because we have the Northeast Probability Seminar. So if you're interested, you can switch into or go into that seminar. We will meet again in 4 weeks. So we will have Peter Fritz on December 4th. Okay. Okay.
Thanks
so
for having us.
Thanks for
Thank
everybody
you.
for joining, and I hopefully see you in 4 weeks.
Bye,
Okay,
Carsten.
bye-bye. See you.